Okay, good afternoon, and I hope you all had a nice weekend. So we continue with second part of the 2 weeks of classes on General Chemistry 2. And before we continue with the chapters, there's first a recapitulation of the chapter 12 and 13. These slides were given to the teaching assistant and probably will be sent to you afterwards. So I think we will need probably 2/3 of today's class, and then we will continue with chapter 14. So these are the most important things about kinetics. So first of all, it's about the speed of the reaction, the rate of the reaction, which you could see as the disappearance of the reagents or the growing of the product as a function of time. We can define the rate equation and K, small k, as a rate constant. And we also discussed what it means, the order, or maybe the global order of reaction. This has to do with the molecularity. We have first order, second order, and those were the two types that we discussed the most. And so, in fact, X and Y combined is the global order of a reaction. Now, depending on whether it's first order or second order, we have different kind of graphs that we can see of the concentration in function of the time. Now, this is a typical graph of the concentration of the reagents in function of time. This is not immediately leading to a conclusion. If you make a logarithm and it's a straight line, then you can conclude that it's actually a first order reaction. If, on the other hand, it is a second order reaction, then plotting a reciprocal concentration over time gives also a straight line, but an ascending straight line like this. And so in the slope, it is now the rate constant. And we have also discussed what it means half-life time. So this is the time that is needed for the concentration to fall until half of the original concentration. And for a first order reaction, this half-life time is a constant, is actually ln2 divided by k. For a second order reaction, this is time. This is actually dependent on the concentration, so it's not a fixed half-life time. That's only for the first order. Going on with the most important things. So we have shown that the rate constant is constant as long as you don't change the temperature. If you change the temperature, it is varying. In fact, it's if you increase temperature, you always increase the rate constant. And for that, we have the Arrhenius equation, which says it's a pre-exponential factor A multiplied by exponent with ground number E to the minus activation energy over RT. So since activation energy is always positive, this means with an increase of temperature you have an increase of K. And this is another way of writing the Arrhenius equation, like ln K2 over K2. And from this you can determine the rate constant at any temperature, as long as we have it at one particular temperature and we have the two temperatures and the activation energy. Then we discussed two different theories, the collision theory and the transition state theory. In the collision theory, we actually have three factors that govern how fast the reaction is going, and that's the concentration, and that's a frequency factor, so it's R. The F is an energy factor, similar to in the Arrhenius law, and P is a steric factor, which you can say is equal to A, more or less. So for the transition state theory, we have defined reaction progress in function of the energy profile, and in fact the reactants and products are minima, local minima on that profile. The transition state is maximum on that profile. And to get to that maximum, you need to invest the activation energy. And one way of getting this activation energy, of course, is via collisions. So in fact, the collision theory and the transition state theory are not mutually exclusive. In fact, they point in the same direction. So you see the activation energy here, going from here to here, is actually larger than going from here to here, since it is an endothermic reaction. So here are some more reaction profiles. So between reactants and products, we have a local minimum. It's an intermediate. So this is now a more complex reaction, not going via one step, but there are several elementary reactions. And sometimes there is a high energy intermediate in between. And typically of intermediates, that's different from a transition state, it is a minimum. Transition state is also always the top of the mountain, whereas an intermediate is, let's say, somewhere like a valley. So, indeed, these are two elementary reactions after each other. The rate determining one will be step number 2, because this has the largest activation energy. We discussed this activation energy, the largest meaning this is the slowest step, and therefore will determine the rate of the reaction overall. One way of speeding up the rates of reactions is adding a catalyst. And in this graph we see another reaction profile with the reaction progress in the x-axis. So the green line is an uncatalyzed reaction, the red line is the one going via a different mechanism involving again an intermediate. The intermediate is here, and both activation energies are actually smaller than the activation energy going via the uncatalyzed reaction, so this is certainly going to speed up your reaction. And we also talked about homogeneous versus heterogeneous catalysis. The main purpose of catalysis is lowering activation energy and therefore speeding up the reaction without having to invest a lot of energy. So I left a few assignments at the end of the chapter on kinetics, and one of them was more a theory question, and it says, okay, discuss the factors that determine the reaction rate according to the collision theory, and indeed there are three factors, R, F and P, with R being the collision frequency, and therefore the chance of two particles X and Y meeting each other, and that's of course directly proportional to their concentrations of X and Y. So this is something that we already see in the rate equation, because concentrations are in the rate equation. Of course, it's only the concentrations that are important in the rate determining step that you will notice here. Then F is an energetic factor, and that's the amount of collisions that have the right energy. That has to do with the Maxwell distribution at a certain temperature. So this is indeed this E factor of minus EI A over RT. And that's typically going to be a number between 0 and 1. So if your activation energy is very large, it's going to be close to 0. If it's very small, it's going to be close to 1. Of course, your temperature also has an influence. And then it may be that your particles have sufficient energy, but that they do not approach in the right way. That's the steric factor. So, and certain transition states are very ordered, and in that case, it's going to be difficult, and your P factor will be close to 0. Others, it doesn't matter. Any collision is actually giving a product. In that case, it will be close to 1. This is another more theoretical question. We are asked to look at a couple of phrases and discuss what we think about it. So the first phrase is that Arrhenius constant A agrees with the value that K, the rate constant, would have if all collisions were sufficiently energetic. So if all were sufficiently energetic, so that means T is actually, the temperature would have to be infinite, or EA would have to be 0. That's the only case in which you would have that. And if that is the case, this factor is indeed 0. So a very, very, very small, approaching 0. And in that case, of course, e to the minus 0, that's 1. So we multiply a with 1 and we get indeed a. This is indeed a true statement. A second statement says that there is a relation between Arrhenius constants, A, again, and the orientation of the reagents during a collision. And I think we can also conclude here that this appears to be correct, because the orientation is a steric factor P, and actually P equals A. So you see how the two theories, collision theory, Arrhenius law, are related. And then the third statement is that there is a relation between A, the Arrhenius constant, and the entropy of activation. And also that we have seen in the theory, that entropy of activation, delta S, with double cross. So that's a part of the free energy of the activation here. Which is actually independent. This is actually nothing else than the activation energy. So that means we actually have the same kind of relation as in the Arrhenius law. And that means that the entropy is directly related to A, the Arrhenius constant. It's not a one-on-one, but they are related to each other. Also that we have seen in the slides. But this is, I would say, something a little bit less theoretic. So this is just a question about the format of the rate equation based on experimental results. And these are the initial rates of the reaction, and the reaction is between bromates, bromide, and acids. And the initial speed is given in the first line. In the second line, we double the amount of bromates, and we see that we actually double the speed, the rate of reaction. So we can conclude that the bromates is first order, the concentration is first order in the rate equation. have doubled again, but now the bromide concentration, this remains doubled. And we see that we double again, the speed now is 3.2, 10 to the minus 10 to the minus 3. So in the fourth line, we have doubled the proton concentration, and we keep the rest. But we still see it's 3.2, so we have not doubled, but we have quadrupled our speed. That means now this is second order in protons. So that means we actually have a rate equation, quite special. This is a fourth order reaction. Because the global order of the reaction is 2 plus 1 plus 1. So actually fourth order is quite exceptional, because normally reactions are either first or second order. This is a question about aspirin that is metabolized in the body, and this behaves like it is a first order reaction. So based on the concentration of aspirin, the half-life is 3 hours, and we know that for first order reactions the half-life is constant. That should allow us to do some calculation. So the time and a half so is 3 hours. So that means K, if we express it per hours, is ln2 over 3 divided by 3. Okay, so we want to know what about how much is left after 5 hours, and we have the general equation ln a minus x is ln a minus kt, t being the time. So this is 5k because the time is 5 hours. So that means we can actually write it as 5/3 of ln2. So this is actually bringing the same thing here. Okay, so some simple mathematics, and a over x over a then is 2, so we just integrate everything, 2 e to the minus 5/3, so this is the factor that we still have remaining. So this is 1 minus degree of conversion. So this is the fraction that is remaining. It's if you express it in percentage, it's 37.8. The percentage is still remaining. Okay, so now, so we have substituted, maybe I went a bit too fast, but we have substituted, K is 3 over ln 2. So we have substituted that here. We have it in the first line. So, how much does that make it that we still have left? Well, we started with 200 milligram of aspirin. So, this amount of that is still left, which is 1 minus degree of conversion, has to be multiplied by the amount at the start. So that means we now have about 75.6 milligram left of our original 200 milligram, which seems about right. So if you know that after 3 hours it's going to be half. So normally after 6 hours it should be about 50. So this sounds to be more or less correct. This is another exercise, one that I think I didn't give to you, but you can just treat it in the class. So this is about a sample reacting. After 45 seconds, we actually have 90% left, so that means 10% has reacted. So suppose it is given that this follows first order kinetics, then what can we tell about the half-life? So, and first order kinetics, of course, we have the same kind of formula still operating, so ln A minus x is ln A minus kt. So let's apply that for the situation at 45 seconds. So that means that A minus x at that point is 90% of the original A, or 0.9 A. So we could calculate k from that, because that means logarithm of 0.9a is logarithm a plus logarithm 0.9, so which is minus kt. So ln 0.9 is minus 0.1054. So we can calculate t from that. All of the rest is known. So then it follows that k is 2.34 10 to the minus 3 per second. That's k. Now we have to calculate the half-life, but that's easy. That's just ln2 divided by k. And ln2 is 0.693. So if we divide that, it's going to take 296 seconds to reach the half-life, which again seems to be kind of logical, yes? This is another one based on some experimental data. So we need to apply these formulas that we have seen for having Ks at two different temperatures, having activation energies, and then making calculations from that. So it's a reaction of nitrogen pentoxide, dinitrogen pentoxide, N2O5. It's decomposed, and we can assume that it's first order kinetics again. So it's in a closed vessel, and NO2 is formed, and oxygen. So in fact, the reaction equation here is not that important. The most important thing is that we know that it's first order kinetics. So, well, we can see in fact that it's first order kinetics because we have the logarithm of the concentration of N2O5, and we see that it is on a straight line, although of course we have very little points. We have only 2 points, and 2 points are always on a straight line. But we can assume that even if there were more points, it would be on a straight line because it's first order kinetics. Okay, so we have some data here. There are two different temperatures, 35 degrees Celsius and 45 degrees Celsius. Again, we shouldn't really hesitate too much. Which curve is the 45? Because at 45 degrees it goes faster. So that's one that should go down more fast than the one at 35 degrees. Okay, so that's why my first question was actually not that difficult. So which line is which temperature? Well, the one that goes down the fastest is the one at the highest temperature. Then, to calculate the activation energy, we need a little bit more, because then we need K1, K2, T1 and T2. The two temperatures we already have, it's 35 and 45 degrees, but we need to calculate the two rate constants. And we can do that from the data that we have here. So this is the equation that we need. ln K1, K2 equals minus EAR over the difference in the reciprocal temperatures. So the two temperatures in Kelvin expressed are 308, that's 35, and 318, that's 45 degrees Celsius. The R that we take is 8.31 because we are now dealing with non-atmosphere calculations. So we need K1 and we need K2 to calculate activation energy. These are still unknowns. Now, ln A we can derive from the data. It's 2.3 minus 2.3. So, and then the next one is minus 2.5 as at 1500 seconds, and at 1600 seconds we have at a different temperature minus 3.1. These data now we can use. So after 1500 seconds, that's the one at the colder temperature, and A minus X is 2.5. That's the value that it became. So that means 0.2 is 1500 K1. So K1 is 1.33 10 to the minus 4 per second. And you could do the same calculation for K2. And then you see that indeed this 10 degrees makes a lot of difference, because now it's not 1.33 but 5 10 to the minus 4 per second. And this is a general thing. If you heat 10 degrees Celsius, your rate actually is multiplied by about 3, depending on, of course, what is the activation energy. But on the average, it's heating 10 degrees, your speed goes up 3 times, so your time that you need for the reaction actually to reach the same result also drops 3 times. So if you put all of these data in the formula above, you reach at an activation energy of 107.8 kilojoule per mole. So we apply the T1, 308, the T2, 318, K1, 1.33 10 to the minus 4, and K2, 5 10 to the minus 4. So these are all applications of the formulas that we actually have seen. So, okay. Good. Now we give the recapitulation of another chapter, which was a little bit longer. We're going to spend more time for the recapitulation on that one. So chemical equilibrium, some of the concepts. We have seen that many reactions do not complete, but to reach a certain equilibrium state where there is a mixture of the reagents and the products in varying composition. It could be mostly products, but also there are situations where there's very little products being formed. So to express how much actually this has occurred, we can use the degree of conversion, but most chemists would like to prefer to use the equilibrium constant K as a measure of the conversion. In fact, both can be related to each other in some cases. Since in this chapter we mostly discussed reactions in the gas phase, we could define both Kp, and these are the ratios of the pressures, or we could define Kc, which is the ratio of the concentrations. And these are the concentrations or the pressures of the products, and this is then with an exponent that equals their coefficient in the reaction equation. This is then divided by the concentrations of the reagents. Again, there may be an exponent that goes back to their coefficients. We explained also that there are heterogeneous equilibria possible, and that in such equilibrium the species that are solids or liquids are not in the concentration or in the pressure dependent parts. So they do not occur, in other words, in K. This, in many cases, simplifies the equilibrium constant a lot. We have learned also how we can use K, the equilibrium constant, to do calculations. For instance, the concentrations that we have of both reactants and products in such a mixture. We have seen also how we can thermodynamically combine equilibrium constants. By adding up reactions, we can also then make a new K, then we use either the sum or the ratio of the K, and we might also again have an exponent based on the amount of reactions that we combine together. We saw a few examples. And then in red is one of the most important equations here. This gives the relation between free energy and the equilibrium constant. It's a standard free energy, in fact, free energy change of a certain process. It's related to its equilibrium constant. And you see also that there is a temperature dependence. Then at the final stages of this chapter we have also seen that there can be a kinetic approach to the equilibrium, and in fact there are two reactions going on at the same time. The reaction from the reagents to the products, but also there is a reaction from the products to the reagents. Each of these two reactions have a rate constant, and the ratio of these rate constants is actually nothing else than the equilibrium constant. Okay, and at the very end, we have also seen that we have the law of Le Chatelier, which means that if we have some kind of change to our reaction conditions, the equilibrium will shift in such a way that this change is attempted to be undone. We have seen the influence of temperature, concentration, and pressure. So these are typical ways how the equilibrium constant would be written for any kind of reaction with any kind of coefficients. And you can see Kp and Kc are actually related to each other. So to get Kp, we need to multiply Kc with a number of factors of Rt. And this is an exponent delta n, and with delta n, the amount of gas moles that actually it has increased. If there are no gases, or the amount of gas molecules has remained the same, then Kp and Kc are identical. So Kp we will only use when there are actually gases around. If you have reactions in solution, we will use Kc. And indeed, as already mentioned, we can do a lot of calculations of K on the concentrations, or make concentrations or calculate concentrations from a known K. Here are some examples where we could have relations between reactions. So if, for instance, the third reaction is the sum of reaction 1 and reaction 2, we actually will multiply the corresponding equilibrium constants. If the third reaction is reaction 1 minus reaction 2, it's actually going to be the ratio of K1 and K2, that is the new equilibrium constant K3. When a certain reaction is used more than one time, maybe 2 times, we need an exponent to express that. So for instance, if reaction 3 is 2 times reaction 1 minus reaction 2, then we actually will have the square of K1 divided by K2. And this is all the result of the logarithmic relation between the free energy and the equilibrium constants. Because free energy we can just add up. But of course, here, if we add this up and we add logarithms, that means we have to make the sum, the product. And the logarithm of the product is the sum of the logarithms. Very simple mathematics. So let's give a simple example. It's one from the solubility equilibria. So we have several weakly soluble chlorides, including silver chloride and lead chloride. So they split partially into ions, silver plus and chloride minus, and lead 2 plus and chloride minus. But now we could consider a third reaction, in which lead chloride is combined with silver, and this might exchange for silver chlorides and lead 2 plus. So it can be shown that the third reaction is actually reaction 2 minus 2 times reaction 1. That's the way how we can exclude free chlorine. Because we don't have chlorine, in fact, in this reaction. So we eliminate chloride anion by combining the two reactions in this way. This is how we could see it. So reaction 2, then minus 2, reaction 1. So we know that minus coefficient means we bring it to the other side. So I really write it here step by step. And indeed, you can see that it's actually true. So the chlorides have actually been taken away in that way, because they compensate each other. And so we have made our third reaction. Just if you do that, be careful that you only are combining the same entities. I have seen students doing, for instance, let's take CO2 and subtract CO, and then we get carbon, or we get oxygen. That's not correct. Yes? You can only subtract the same species, so chloride and chlorides. So that is possible. And indeed, negative coefficient means you go to the other side of the equation. So, okay, if we now know this, it means for a third reaction, for the free energy, it's actually the same way. So free energy of first reaction minus 2 times the free energy of the free energy of the second reaction minus 2 times free energy of the first reaction. So let's now convert it into the logarithm of k, just to show you how actually these mathematical relations are there. So that's every time it's minus RT ln k for every free energy. So of course, in the case of the delta G1, it's going to be 2 times RT ln KSP of silver chlorides. This is actually going to become plus because it's minus and minus combined together. So let's make it a little bit less complex and divide everything by RT. In fact, divided by minus RT, then we see that ln K of the third reaction is ln K of the first reaction, or in other words, ln KSP of lead chloride, minus ln KSP of the first reaction, that's silver chloride. So this two we can bring in the logarithm, but then we have to square the silver chloride's KSP. So the logarithm of the square of a certain number is 2 times the logarithm. Okay? So now we actually can, like you could say, integrate that, or in fact everything now is converted from the logarithm to the ground number of the logarithm. That means now it's K3. And so this is KSP, lead chlorides. And because there's a minus number, this is the reciprocal. So we divide over this. And it's the square, because we already have that. This is, if you know, take the logarithm, it's the same thing. A logarithm of A over B is logarithm A minus logarithm B. So this is how we arrive at it. I'm sorry if I bore you with this simple mathematics, but some people sometimes have problem with it. I just repeat it. So, what about the kinetics, thermodynamics, and the equilibrium constant? So they're all interrelated. So we can draw a graph of the free energy in function of the reaction coordinates, as we have done already a lot of times. In such a graph we can notify the activation energy, and there are always 2 activation energies. So depending on from which side we are going over the transition state, it could be different. This activation energy is important for the kinetics because it governs the rate of the reaction via the Arrhenius law. So EA is always positive, that means K is always increasing as the temperature is increasing. So that means this is the part that you could consider kinetics. For the thermodynamics case, we have these very important equation, which we can also write like that. If you don't like logarithms, we can write it as a power of E. It's actually the same. So if you take the logarithm of that and you put the RT on the other side, the minus RT on the other side, you get the same results. So delta G can actually be positive or it could be negative. So that's different from the activation energy. Activation energy is always going up, but delta G could go down, could go up. Of course, spontaneous process means it's negative or exergonic. But you do have also non-spontaneous processes with positive free energy. When the temperature rises, the K, equilibrium constant, may increase or decrease. We actually, without having more data, we cannot say which one it will be. It actually will depend on the different factors of enthalpy and entropy. So this you could consider to be an integral part of thermodynamics of a reaction. Now this graph of the free energy in function of the reaction coordinates, we have one here. So this is a typical exergonic reaction, meaning the products have a lower energy. So delta G is negative in this case. And you see here the rate constants. I have made a distinction between the rate constant going from the left to the right and from the right to the left. And so the activation energies are also different in that case, because if you go from the left to the right, you see the activation energy is much smaller than if you go from the right to the left. So that means the K will be quite different. And actually, we can predict delta G is negative, and therefore the reaction is probably going to be strongly to the products because of that. Because the reaction going to the products is much faster than the one going back, due to the smaller activation energy. And the way we express that is actually by making the ratio of the two. And so if this rate is a lot faster than this, we're going to get a big K, and we're going to have mostly products, and most of the reagents will be gone. Substrates, it's the same as a reagent. Reagents, ground states sometimes is exposed states. So the delta G is this here. The difference between the levels of the starting material and the level of the products. It could go down, but there are other situations possible. Okay, the thermodynamic equilibrium constants. Again, the same formula we see here. So the principle of Le Chatelier, we also mentioned at the end. So we go to the direction where our change is produced. So that means for endothermic reactions, when you heat them up, you go to the products. And that's one of the things. And this we can actually see in curves that show the temperature dependence of K in function of the 1 over the temperature. And you can see that for exothermic reactions, so this is cold, this is hot parts. So at the hot parts, so we actually have an LNK which is not that good. And so here we have 1 over T which is small, and LNK is large. I need to check these figures, but okay, I will see it in a moment. So here we can see why it is the enthalpy which is important. Because you can split up the enthalpy and the entropy parts. And this is another way of writing the thermodynamic equilibrium constant. So we split it up in an enthalpic and an entropic term, and it's only the enthalpic term which contains the temperature. So if you take the logarithm, we actually see it's this kind of function and delta H over R is actually the equilibrium constant, or the slope, sorry, the slope of the reaction. Delta SR is not dependent on the temperature, it's actually the part that is cut off at 0 from the function with the y-axis. Okay, so we're going to have a small break and then we continue with a few exercises on the equilibrium. If you have any questions, I will be here. Okay, on the last slide I noticed something wrong, so I decided to make a correction. Maybe if you have this slide, exothermic and endothermic was actually interchanged by accident, so I put it back on the right place. But how do I know that it was wrong? In fact, endothermic means delta H is positive. And if delta H is positive, minus delta H over R is negative. So that means your curve goes down. If delta H is negative, it's actually exothermic. Minus delta H over R is then positive, and that means you now will go up as it is shown there. So that's why I was looking at it and I said, must be something wrong. Okay. This actually is something that looks very similar to a similar formula for small k, which we applied in the exercise, but now it is also for large k, and now the enthalpy takes the place of the activation energy. So we can use the same formula. And we can use it either to calculate the enthalpy of the reaction, or if you have that and we have the temperatures, we can calculate a new K from another K at another temperature. Okay, so this is our first assignment after the equilibrium chapter. So it's about the acetate ion, which partially transforms into acetic acids. You see, I still have the same mistake that I corrected in the exercise, but not in the solution. Obviously, we're going to correct this. Fixed. Okay, problem fixed. Just wait for it to show up. Okay, acetic acid, not acetate. Anyway, so this is an equilibrium that is, as it is expressed, far to the reagent. Only a small amount is actually hydrolyzing. Only a small amount of acetic acid and hydroxide is forming. So, and it is given that in 0.1 molar solution of sodium acetate, the conversion of the acetate at 25 degrees is only 7.5 10 to the minus 5. So only 7 molecules, 7.5 molecules in 100,000 are actually hydrolyzed. So it is asked to calculate from this data the value of the equilibrium constants. So what we should do first is try to find the relation between the alpha, the degree of conversion, and the K. So the conversion formula can be seen that it is alpha square concentration divided by 1 minus alpha. How do you know that? The water is not taken into account, it's a solvent. The concentration after the reaction of the acetate is 1 minus alpha C, we see the concentration. And the concentration of both acetic acids and hydroxides is the same. It's alpha multiplied by concentration. So that means if we now make K, it's alpha concentration multiplied by alpha concentration, so that's alpha square concentration square, divided by 1 minus alpha concentration. We can reduce the concentrations, and we finally end up with alpha square concentrations and 1 minus alpha. So we can fill everything in. We can also simplify, because 1 minus alpha is actually the same as 1. Because alpha is 7.5 10 to the minus 5. That's not significant as compared to 1. So we can just put this 1. So we now have K is alpha square concentration. So, and we know what is the concentration, is 0.1 mole per liter. And we know what is alpha, so we fill it in. And that means we now can simply calculate K, and that's 5.6 10 to the minus 10. Indeed, a very, very small equilibrium constant. And this is normal when we assume that there will be very, very little conversion. So here it is asked to calculate the value of equilibrium constant of two different reactions, and we want both Kp and Kc. So it's at 25 degrees and it's at 1000 degrees Celsius. So, and the two reactions are NO being oxidized by dioxygen to NO2. And the second one is the decomposition of calcium carbonates, a reaction we have encountered already a lot of times. Calcium oxide and CO2 is formed. So, what is the methods to do this? And so it's based on the thermodynamic equilibrium constant. That means we need the free energy to be able to calculate the K via delta G is minus RT K. So, and to get free energy, of course, there's an enthalpic term and there's an entropic term. Now, for both of them, we find the data in the book of tables. That's table number 4. So, as usual, like we have done before in the chapter of thermodynamics, we do these kind of calculations. So, and then with a delta G is minus RT and Kp, we get Kp. And then Kp we can convert into Kc by applying a factor of RT. Okay, important is to know what about the moles of gas that are being changed. And we can see that in the first reaction we actually go from 3 mole of gas to 2 mole of gas, so delta N is minus 1. Whereas in the second reaction we generate CO2, 1 mole of gas extra on the product side. So delta N is plus 1. Okay, now I don't give the details of the calculation, but this is just as usual. Delta H is made from the delta H of the formation of the products minus delta H formation of the reactants with the coefficients that are needed. So what we find for the first reaction is that delta H is negative, and delta H is independent of temperature, and that the delta S is also negative. So, in fact, it should not surprise us that delta H is negative, because we lose gas. If you lose gas, you lose disorder, and that will mean you have a negative change of entropy. Now, the free energy will of course be dependent on the temperature. So 25 degrees, that's 298 Kelvin. So if we calculate the delta G at that temperature, it's overall still negative, although less negative than the entropy. So the entropy actually compensates part of it. So we have what you could still consider a rather strong negative free energy. That's good. That's a spontaneous reaction. The Kp is, we can calculate with that formula, and you see it's 2.15 10 to the 12th. So that's a lot. So that's 2 trillion. So that means we have complete conversion, as complete as it can be. Kc, well, in fact, Kc divided by RT is Kp. So if you bring RT to the other side, so that is going to be the value. So it's also a quite big number. So 5.25 10 to the 30th. Okay, so this is clearly an equilibrium that is to the right. So, then what about the same reaction but at a different temperature? It's now at 1000 degrees Celsius. Now the factor of entropy minus T delta S will be a lot larger. And what you can see is actually it is now a positive number. Delta G is plus 72 kilojoule per mole. Kp is now also a small number. So 1.1 10 to the minus 3. And so Kc is then also not that big, 0.014. That means this reaction is going to be more towards the reagents than to the products. So a rather, let's say, we get to switch from a spontaneous to a non-spontaneous reaction, to a free energy that is negative, to a free energy that is positive, or from an exergonic to an endergonic reaction. I think this other calculation we may have done already in the course material, but let's do it again with the calcium carbonate. As you can see, delta H is plus, so that's endothermic. Previous reaction with minus 114 was exothermic, but this is endothermic. That's already not so good for the reaction. Delta S, on the other hand, is positive, 160 and more joule per Kelvin per mole. To be expected, because we create gas, extra moles of gas. Now at 25 degrees, as you can see, the fact that we have the positive entropy cannot compensate for the endothermicity, and the delta G is rather strongly positive, 130.5 kilojoule per mole. This reflects in a Kp that is actually very, very, very small. A factor of 10 to the minus 23. In fact, Kc is comparable. We now have to divide by RT, in fact, because delta N is positive. At 1000 degrees, we now have a negative free energy, which is good. This, in principle, is a spontaneous process. So our term T delta S now has made this sufficiently negative. So Kp is 11.7. It's more than 1. That's the good news. So that means at least the equilibrium will be shifted to the CO2 product. Or if we have Kc, it is 0.112. This is because we have to divide by RT, which is quite big because we are at 1000 degrees Celsius, so 1293. Remember that this R for these conversions is 0.082. Okay, so a similar exercise. So we have methane and water. Water is in the form of vapor. So it's H2O gas. We mix them and there's a partial conversion, meaning we have an equilibrium. What we form is CO and dihydrogen. Now there are several things that are asked. First thing is, at which temperature will we have a Kp equaling 1? Second question is, discuss the influence of an increase of the temperature at constant pressure on the molar fraction of dihydrogen, which is the product. And then discuss the influence of an increase of the pressure at constant temperature on the molar fraction of dihydrogen. I think now it's useful to write the reaction equation. Methane is CH4, it's a gas. Water is in the gaseous phase, I put it in the red to make sure it's water vapor, so we don't have to hesitate, it's in the gaseous phase. And, well, this could be an equilibrium atom, in fact. It gives CO gas and dihydrogen gas. What you can see is that we go from 2 moles of gas to 4 moles of gas. This will have, of course, some consequences. Now, for the first part, we asked ourselves what is needed to have a Kp of 1. In fact, if Kp is 1, ln Kp is 0, because the logarithm of 1 is 0. That means, in that case, the standard free energy change at that moment, when we have Kp is 1, will be 0. And that means at that particular point, we have a compensation of the enthalpy term and the entropy term. So delta H has to be equal T delta S. So it's now actually quite easy to calculate the temperature, because it means you just have to divide delta H standards by delta S standards. And those two things we can calculate. So they're independent of temperature, and these calculations are based on the, again, data that we find in table 4. So I did a calculation for you, just adding up the enthalpy and entropy of formation of all the components. Make sure you use the water-gas parameters and not the water-liquids. So if you do that, you get a value of plus 206.1 kilojoule per mole for the enthalpy. This is clearly not so favorable from the viewpoint of enthalpy. So it's an endothermic reaction. But if you go from 2 mole gas to 4 mole gas, of course we can already suspect that we will have a large entropy increase. And indeed, it's also positive by 218.8 joule per Kelvin per mole. So we can now determine the temperature in Kelvin, we divide one by the other, and take into account that one is kilojoule and the other is joule, because it's a factor 10 to the third. So if we calculate that, we actually will get a number of 942 Kelvin. At this precise temperature, so our Kp is going to be 1. Now for the second part of the question, it was asked what about a temperature increase and what if you keep the pressure constant, what will be the fraction of dihydrogen? And dihydrogen is on the product side, so that means we can now think of, okay, will it be actually going towards the products or will it be going towards the reagents when we increase the temperature? Now, in fact, at the moment when the temperature increases, our T delta S factor will actually be in absolute values be larger than delta H. That means our delta G, free energy, will become negative when we increase our temperature. And the reaction will be spontaneous, means Kp is larger than 1. And that means we move towards the products. In other words, if you move towards the products, the molar fraction of the dihydrogen will increase. You could also answer in a different way, which more or less means the same. You could say, it's the principle of Le Chatelier. So if we have an endothermic reaction, and this is an endothermic reaction, so when we heat the endothermic reaction, we move to the product side. K increases. But actually the explanation is the same. The third question was, if you increase the pressure, what is going to happen at a constant temperature? Now, it's again the principle of the Chatelier. And if we increase the pressure, we're going to shift the equilibrium to the side that has the least particles. Now, we know at the product side we have a double amount of particles than at the reagent side. So we're going to move to the reagents. And that means we shift to the left or to the reagents, and that means now your hydrogen will be taken away. So the molar fraction of the hydrogen will be lowered in this case. In the case where we increase the pressure. If you put the pressure less, at a low pressure, of course, it will be the opposite. In that case, we move to the one with more particles. But it was asked what happens if we increase the pressure. Okay, so this is a more theoretical question, you could say, although you could also give some further explanations. So these are 4 different situations, let's say, for which we should find conditions separately. So the first one is a reaction of which Kp would increase when the temperature would increase. The second one is one where the value of the free energy change at standard conditions would increase with increasing temperature. And this one, the third one, is the value of the rate constant would increase with increasing temperature. Or that the conversion of one of the reagents would increase with increasing pressure. Okay, so let's have a look. So the value of Kp increasing, and that of course reminds us again the law of Le Chatelier. So there's only one condition, and that's in fact that the reaction is endothermic. Or in other words, that delta H is positive. So in that case, Kp will actually increase when the temperature is increasing. You see here some formulas that express the same. And in fact, only the part where delta H is included has a temperature-dependent part. So entropy has nothing to do with the value of Kp increase with temperature. Now, a similar question, but now about the free energy. So we want delta G to increase. So the value of delta G increasing actually means that the K is going down, because the more positive delta G becomes, so the less spontaneous is the reaction, especially if your delta G becomes positive. So, in fact, for delta G to increase with increasing temperature, we actually would require delta S to be negative. And this is possible for a reaction in which we have less gas particles. So in that case, we will get delta G always more increasing with increasing temperature. So, and this also could be seen as an application of the law of Le Chatelier. Now, the third question, you could say, is a little bit of a tricky question. So it was asked, what about the value of small k, the rate constant? What is needed for it to increase when we increase the temperature? Well, the answer is nothing is needed, because this is always the case. Because we know that activation energy is always positive, therefore there is no other option but for K to rise. How much it rises and how fast, that can be dependent. And that can depend on the size of the activation energy. But it has to rise in any case. Then, for the conversion of one of the reagents to increase with increasing pressure, this is actually another application of the law of Le Chatelier. So, we move in the direction with least particles. The condition was that we have more reagents being converted, so in other words, we move to the products. So if you want that the increase of pressure moves to the products, it means the products should have less particles. So the amount of gas molecules in the products should be less than in the reagents. So when you move from the left to the right, you should move to the least particles. So in that case, your pressure will have a positive effect on the conversion. Okay, so here's another exercise. I think this one you didn't get beforehand, but I will just give the answer right away. So it's about sulfur trioxide, SO3. We start with the pure compounds. There's 400 millimole of it, 0.4 mole. And we heat it in a closed vessel. That means the volume remains constant. So this decomposes partially and you form SO2 and dioxygen. And the reaction proceeds at 1000 degrees Kelvin, quite hot temperature, and 0.1 mole of dioxygen has been formed. All of the substances at that temperature are gases. So 27 liters. Now we ask three things. To calculate the value of the equilibrium constants, Kc, at 1000 degrees Kelvin, not Celsius, sorry, Kelvin. To calculate the value of the equilibrium constant Kp at 1000 Kelvin, should be easy, just conversion. And to calculate the degree of dissociation of SO3, alpha, you could say, from the K. Okay, first we need to have a look at the reaction equation. So we see that we need two SO3 molecules, and we get two SO2 molecules out and one molecule of O2. Now, that means it was given that we have at 1000 degrees Kelvin 0.1 mole of oxygen. This automatically means we will have the double amount of SO2, meaning 0.2 moles. So, and these 0.2 moles actually have to come out of the SO3. We started with 0.4 moles SO3, so that means there's actually 0.2 moles left of SO3. So we know in fact the amount of moles of all of the mixture. 0.1 SO2, 0.1 SO3, and 0.2 SO3 and 0.1 O2. So we actually can derive the concentration constant from that. So, it's actually quite simple because the concentration of SO2 and SO3 is the same, above 0.2 mole. We can actually get rid of that. That means only one concentration term is important anymore, and that's O2. So that means Kc is 0.1 mole per volume, 27 liters. So this is 3.7 10 to the minus 3. That's Kc. It's very simple. Not need for a lot of calculations. No thermodynamic calculations here are needed. We just have all of the data. Now, as you can see, we get one extra mole of gas. So that means we have to multiply Kc by the factor of RT. And that is 0.082. T is 1000. So that means, I go back, sorry. We get 0.30 after multiplying with 1000 and 0.08. Now, the degree of dissociation, there's an arithmetic dissociation, is in fact 0.5. It's very simple. Half of the SO3 has been converted. So you could also express it in percentage, then it's 50%. 50-50. This is, I think, the final exercise. It's heterogeneous equilibrium. We start with the solids, sodium hydrogen carbonates. It decomposes on heating. We get solids, sodium carbonate, Na2CO3. We get carbon dioxide and water vapor. So again, vapor. So we have to take water in the gaseous phase. So in a closed system, we reach an equilibrium state wherein the gases are water and CO2. So here we don't really need to do calculations. will just ask a couple of questions. So we want to discuss the influence of an increase of the volume at constant temperature on the value of the equilibrium constant and on the degree of conversion of sodium and hydrogen carbonates. What about increasing the temperature at constant volume at the same factors, value of equilibrium constants? And if you have constant volume and constant temperature, what will happen if we add sodium carbonate? So these are again, let's say, all applications of shifting equilibrium. Now, the first question A, so if we increase our volume, and so then there is going to be no, let's say, influence on the equilibrium constant. Equilibrium constant is only changing when we change the temperature. So as long as you keep your temperature constant, it's going to be a constant equilibrium constant. So this is, you can change your volume, your pressure, all you want. This equilibrium constant remains the same as long as the temperature is what it is. So the degree of conversion, that will be changed. So because that is actually concentration, or in this case, pressure dependent. So higher volume means, because of the PV-nRT relation, means lower pressure. So, more gas could be formed when you have lower pressure. So, and that means that you will actually have a larger conversion. More sodium hydrogen carbonate will be converted if we increase our volume, because there's more place for the particles. But this still doesn't mean that our K will change. Just the conversion that is changing. Okay, so in reaction C, we actually increase the temperature at constant volume, and we want to know what will be the influence on the equilibrium constant. For that, we have to know the thermodynamic parameters of the reaction. So we can calculate that the reaction is endothermic. We can do that from the data in table 4. It's 136 kilojoule, and that's all we need to know. It's a positive value, it's endothermic, so that means if we heat the reaction, it will move to the side of the products. So Kp, in other words, is larger when the temperature increases. Now, what happens if we add sodium carbonate to this mixture? Now, that actually depends on your equilibrium constant. And the equilibrium constant, Kp, is in fact the product of the water concentration multiplied by the CO2 concentration, because these are the only changeable concentrations. Sodium carbonate and sodium hydrogen carbonate are solids. So the equilibrium constant is independent of the concentration of sodium carbonate. That means if you add sodium carbonate, it has no influence on the on conversion. Or in other words, solids or liquids, so they have a constant concentration, as long as they remain in their own phase. So this is a consequence of a heterogeneous equilibrium. as we have here. Okay, so this is the end of the recapitulation of chapter 12 and 13. I'm not going to start on chapter 14, but I think before I do that, I'll just have another break, and then we can start with equilibrium on the acid-base reactions. I'm here for questions.
what I hear. Yeah, I know. A broke ass heterophobic. Đáng nghèo rồi còn heterophobic.
Rồi lại tôm hùm bò tắm, dạo này mấy vụ tôm hùm bò.
Biết chưa xanh quá.
Mất một đống con sắt. Đấy không phải là
Okay, so we move to a different chapter, chapter 14, on which the focus is now on acid-base equilibrium. So other than in the previous chapter, we now are not operating in the gas phase, All the reactions are in the liquid phase, and I think we can even generalize the reactions are in water. And in such a medium, we actually are used to express the acidity as a so-called pH scale. So P is the negative logarithm. But more about that later. But this is a scale that goes from 0 to 14. In the middle we have 7, that's neutral. Anything smaller than 7 is acidic, anything larger than 7 is basic. So if you have just pure water, there are already protons or hydroxide present, because water itself is a weak acid. And what we have is so-called auto-ionization. This itself is an equilibrium reaction, but the equilibrium is very much to the starting material, namely the water itself. So if we describe this reaction, actually the equilibrium constant is the product of the proton concentration, and in most cases I will write it as H3O plus. Sometimes you see also H plus, that's also possible. But normally protons are never free in solution, they're always highly associated with the water molecules. H3O plus being only one of a lot of possible aggregates that you can form. And the other part then, if you take a proton from the water, is OH minus. So for every H3O plus there has to be an OH minus. And this is the expression for the water auto-ionization equilibrium. Now at 25 degrees Celsius, this value is 10 to the minus 14. And this already gives an explanation how come that the scale of pH is from 0 to 14. So very low number, and that means we actually have a very low concentration of H plus and H3O plus forms. So if you take a logarithm of 10 to the minus 14, we actually get minus 14. So that's not very, let's say, easy to work with negative numbers. This is why we take the P H and not the log H. In that way we get always positive numbers, at least in the normal, let's say, concentration ranges. This is the case. So hydronium, that's another name for H3O+. So hydronium ions, and there the negative logarithm, we get a positive number as long as your concentrations are, let's say, not too much. We can also define, but this is used much less, the POH. And that's the negative logarithm, of course, of the OH minus, the hydroxide concentration. And we can actually say that at 25 degrees, if we add up the two logarithms, negative logarithms, we actually have the negative logarithm of Kw, the water auto-ionization, and in other words, that's 14. So that's why we have the scale of 14. So within this range, we have the normal pH are situated. So now, this is actually only true at 25 degrees room temperature. I think most of the reactions that we will see will be at this temperature, but you have to realize that at higher temperatures, the Kw is actually rising. With what we know from the previous chapter, this tells us that the auto-ionization is actually an endothermic reaction. And endothermic reactions have increased their K when you increase the temperature. So in fact, if you have the temperature of the water very high, maybe more than 100 degrees Celsius, and you keep it at high pressure so that it doesn't boil, it can become so that your concentration of the H3O plus becomes quite strong. And for instance, a metal reactor could start to react with the acid protons that you have at such a high temperature. But at room temperature and even at body temperature, this is still, even at such temperature, not going that fast. But in what follows, we assume always room temperature. So, except water, we have also a lot of other molecules that can ionize and give off protons. And according to the, let's say, Brønsted-Lowry acids theory, this is just, we find a kind of acceptor for the protons. And the acceptor in this case is the water, which turns into H3O+. And that means that HA, which is the original weak acid, will give A-, that's the anion, and that's the residue of the weak acid. So if you look at this general equation for the ionization of weak acids, again we see that the water that we have there is not going to be present in the equation. It's a solvent, so it has a constant concentration. That is why we don't need to mention it in our equation. So the only reagent that we need to mention with a changeable concentration is the weak acid itself. And then we have, of course, the anion, A- and the H3O+. They are on the products itself. So this is the typical equation for the equilibrium constants of an acid-base reaction. Now, of course, we also have bases. Bases interact with water. What the base does is it's actually taking a proton from water, and water functions as an acid. What you get is a protonated base and the OH-. Now, as you can see, we have again water as a non-changeable concentration. So the equilibrium constant is going to be of the same form. So the two ions that are forming divided by the concentration of the weak base. We have some tables in the same book of tables about the basicity and the acidity of certain substances, the ones that we need for this course. And we have the ionization constants. So they're as K, HA, or KB, and we also have their negative logarithms in some cases. Now, it's an equilibrium reaction, so we can look at the degree of conversion. And so, in the case of such a reaction, it's the degree of ionization. So, how much ions are actually forming. And these are weak acids and weak bases in general that we are considering. So, actually, alpha in general will be relatively small, a lot smaller than 1. And well, as we have seen earlier, there is actually some kind of relation between the equilibrium constant and the degree of conversion. Alpha square concentration divided by 1 minus alpha in this case. What does this tell us? Well, the ionization increases when the concentration is small. In other words, if we dilute our weak acid, there's actually going to be more parts that is going to split into ions. If we concentrate our weak acid, it's actually going to be less ionized, relatively speaking. So the degree of conversion is going to go down in that case. The constant, of course, is going to remain the same as long as we don't change the temperature. But the degree of conversion is concentration to temperature. So, if we have salts that are derived from weak acids and weak bases, we can actually look at the reverse reaction, which is called the hydrolysis reaction. This means we take up a proton or we add hydroxide. And so in the case of an anion, which is the residue of a weak acid, so taking up a proton regenerates the weak acid HA, and you get also hydroxide. So again, water we should not count, it's a solvent. So the equation for this is now the two things that are formed, HA and OH minus, divided by the A minus concentration. Now, for hydrolysis constants, you will not find any data in the book of table. This is why the reason is that you can derive them from other data that are present. And you can see why. So we can actually add H3O plus on the both sides, above and below the ratio. And if you see the combination of HA, A minus, H3O plus, this is from these three concentration terms are for the ionization of HA, are these the products, and this the reagent. That means it's reciprocal equilibrium constant of the ionization. OH minus and H3O plus combined is KW, the auto-ionization of water. So that means we now actually can take the ratio of the auto-ionization equilibrium constant and the KHA and calculate the hydrolysis constant. And this is why we don't need to have values in the table. We can actually calculate them. And this is another application of combination of reactions. It's actually reaction 2 minus reaction 1. So, if you have a protonated weak base, for instance ammonium, it's protonated ammonia, ammonium NH4 plus, can give away its proton to water, and what you form is hydronium H3O plus, and you regenerate the free base. So we can do the same. This is the form that equilibrium constant is taken. We multiply now with OH minus. This is KW, and the combination of these three terms is the reciprocal base constant, base ionization. So again, KW divided in this case now by KW, KB, the base ionization constant. Okay, so these are reactions related to acid-base equilibrium. So hydrolysis, we can also talk about degree of conversion. So instead of alpha, normally we use gamma, but it's actually not really different. If you want to use alpha, it's also okay. But in this case, so the concentration of A minus that is remaining is 1 minus gamma concentration. The HA that is forming and the OH minus that is forming is gamma. So that means we actually have a conversion like this. This is very similar to the exercise that we saw previously. And now with this formula you can calculate K if you have gamma, or calculate gamma if you have K. So this is, of course, if the anion is a stronger base, you can expect that more OH minus will be formed. You will have more conversion, and so this is actually also to be expected. Also increased by dilution, because we have this concentration term here. That is to be expected, as we have seen previously. So these are a few relations between the different reactions. So we have seen that we can, if we have the hydrolysis constants, it's Kw divided by Kh by the ionization equilibrium constant. So we can bring them to the same site. So if you multiply the ionization constant with the hydrolysis constant, you actually arrive at Kw. The same thing for the base ionization constant and the hydrolysis of the protonated base. Also, if you multiply these equilibrium constants, you arrive at the autoionization of water. You could take the negative logarithm, and then negative logarithm of the autoionization of water is 14. So that means the negative logarithm of the ionization of a weak acids and the negative logarithm of the hydrolysis together add up to 14. And the same thing for the ionization of a base, negative logarithm plus the negative logarithm of the hydrolysis also add up to 14. This is only true at 25 degrees, because we have the 10 to the minus 14 for the autoionization equilibrium constants. Now, as you know, acids react with bases, and we could write it in general between HA and B. So you will actually see that between weak acids and bases, this will not be very high. Between stronger ones, it will be less the case. So you see all of the concentrations here, both on the reagent side and the product side, are changeable. So now we can actually write this as such. Now, this conversion, maybe I didn't give the details, but what it actually means, we have here we can multiply 2 times by Kw, and Kw is H3O plus concentration by OH minus concentration. We do it here, and we get Kw, and the H3O plus concentration, OH minus concentration is needed to have KHA and KB. So in that case, it is actually matching. So if you would fill in the values here, you would actually see that it is is true. Okay, so there's again a mathematical relation between the base constant, the acid constant, and Kw, and the equilibrium constant of the neutralization reaction, because that's what it is called. The reaction between an acid and a base is a neutralization. Now, how it actually looks like is going to be very dependent on the strength of the acid and the base. Suppose we have a strong acid and a weak base. The definition of a strong acid is that it is completely ionized to H3O+. So in such a case, we don't write anymore HA, but we write H3O+. So then your reaction is actually base plus H3O+ gives protonated base and water. Your K is protonated base over base concentration H3O+ concentration. If you look at this carefully, you will see that this is actually the reverse of the hydrolysis constant. So, because the reagent of the hydrolysis is BH+, the results, products, are base and H3O+. So it's 1 over hydrolysis constant. And we know that hydrolysis constant is Kb, the base ionization, divided by the auto-ionization equilibrium constant of water. So the reciprocal is just interchanging. Now it's Kb divided by Kw instead of the other way around. Now, strong base and weak acid. Strong bases convert completely water to OH minus. So it's actually logical to write OH minus now instead of B. And then the proton is taken from HA, you get A minus and water. Again, the water plays no role. And you can see that this is actually going to be 1 over the hydrolysis constant of the A minus. Or in other words, K HA divided by Kw. Very similar to the basic hydrolysis. Now, what if we add strong acid and strong base? This is a reaction that will be completely to the right. And if you look at it, the product is water. So there are no products in the equilibrium constants. It's just 1 over the two reagents, H3O+ and OH minus. If you look at this, this is the reciprocal auto-ionization equilibrium constant of water. It's 1 over Kw. Or in other words, at room temperature, 10 to the 14th. That means completely to the right. And that's of course what we expect. So if you have a strong acid and a strong base, the reaction will be totally complete. What about displacement reactions? We can do such displacement reactions with acids and with bases. Let's look at several cases after each other. H3O+ is actually referring to strong acid. A minus is referring to the residue of a weak acid. Now we can expect, that is well known, that the weak acid will be formed from its salts by strong acid. So what is formed is water and HA. So what is equilibrium constant for this kind of reaction? Well, if you look at it, it's actually the inverse of the ionization of HA. Products and reagents are interchanged. So it's 1 over KHA, and KHA is typically a very small number, so that means the reciprocal is a big number. So if you have 10 to the minus 6, now it becomes 10 to the 6th. So that means we can expect that this reaction is almost completely occurring. What about the base? Same thing, we have a protonated weak base, BH+. We add strong base, OH-, we form B and water, 1 over Kp. Again, is expected to be a big number. So it means a strong base displaces a weak base from its source. That is the expression how it is being done. In exercises, very often we do pH calculations. They're based on the equilibrium constants that we find in the literature. In fact, it actually depends on the strength of your acid. If you have a very strong acid, like ACl, we have a complete conversion and formation of H3O+. In that case, you calculate the concentration of H3O+, you take the negative logarithm, and you're done. Suppose we have 0.1 molar of ACl, that means 0.1 molar of protons, that's 10 to the minus 1 molar concentration, so the negative logarithm is 1. pH is 1 in such a case. To give an example. Now, if you have a weak acid, you're going to need a little bit more work, because now we have to work with the tables and with the equilibrium constant that we can find over there. So here we have the general way to do it. There's a certain concentration of the weak acids, concentration HA. There's H3O+ already present in the beginning from the auto-ionization of water. Now, in most cases, this is going to be very small as compared to the H3O+ that is forming from the ionization of the weak acid. But anyway, I take it into account. There's a small amount of HA that is going to be converted to H3O+ and A-. Again, because we would like to do simplification, we put this as X. So X is disappearing, and X is forming, and also X, HCO+ is forming. That means our original concentration now is no longer CHA, but CHA- X. Okay, so we put that all into our equation. So that means now we have X multiplied by this small amount of H3O+ that was already there, plus the amount X. And then here we have the concentration HA- X. In principle, we should now, if you have all of these data, be able to calculate X out of it, but of course, to avoid any kind of quadratic occasion, it's good to be able to simplify. So, let's assume a few things. They may or may not be true, but in most cases, they will be correct. So, let's first of all assume that this 10 - 7 concentration of H3O+ is not relevant as compared to the H3O plus that will be forming. So in that case we can already omit that. Let's also assume that our concentration of the free acid, the one that is not ionized, is much larger than the part that is ionized. In that case, this becomes a lot easier, because now this term is x, so we have x squared, and this term we omit x, so we have just the concentration of HA, and this is something that we know. So now we have just x squared divided by the concentration of HA. We bring everything to the same side, so that's the product of the concentration with the equilibrium constant. That's x squared. That means we take the square roots to arrive at the proton concentration. And this proton concentration, if we then take the negative logarithm, we have the pH. So from that, this is stepwise methods to determine the pH of a diluted solution of weak acid. We need the concentration, and we need also the equilibrium constant. The concentration is a given, and the equilibrium constant we need to find in the tables. We could ask ourselves, can we calculate also alpha from that? Actually, we can, with pretty much the same calculation, because this is the amount that has been converted, which is x, divided by the concentration, which we started from. That's the same kind of thing. So, we can then fill in this for x. We divide with concentration HA. So actually, we get this. So we still have to take the square root, but now we take the square root from the ratio of the equilibrium constant and the concentration. So with the same two data, we can get both the x concentration H3O plus and the degree of ionization. Let's take some examples. So the first example is the calculation of the pH of 0.1 molar concentration of acetic acid. Acetic acid is an organic acid which is relatively weak. It has an ionization constant 1.8 10 to the minus 5. And with the simplified formula, we can actually calculate that x should be 1.3 10 to the minus 3. And we do that by taking the square root of the concentration, 0.1, and multiplying by 1.8 10 to the minus 5. Okay, so we take the negative logarithm of 1.3 10 to the minus 3, that's 2.87. So it's way below 7, so we can consider this an acidic pH. That's to be expected when you have a solution of acetic acid. Now, we started, so the ionization can also be calculated. It's actually 0.013 degree. So 1.3% in fact is ionized of the compounds. So that is, let's say, not a very large part of the acetic acid is ionized. So that also means X is small. as compared to the original concentration. So 1.3%, that's not a big mistake. Okay, so second example, we have a pH, the same concentration, 0.1 molar, but now the acid is actually hydrogen sulfate, which is actually an acid constant of 1.2 10 to the minus 2. That's a relatively strong acid. Not exactly strong because it still will not be completely ionized, but relatively strong, and in fact this is not applicable to the simplified formula. So what you get is 3.5 10 minus 2, and this is 35% of the original concentration. So what do we need to do when we have a certain situation like that? First of all, we could solve, like it is shown here, the quadratic equation, but then you need maybe more advanced calculator. That could be one thing. Not everybody might have that. There is what is called, and I will get back to that in the recapitulation parts, but it is called the iterative methods. It means stepwise methods. What do you do? So you do the calculation with simplification. And then you take the value of x here, 3.5, that you calculate. You know it's not correct, but you put it here, in this x. So this will mean now we don't put 0.1, but we put 0.065. Yeah. And we calculate again. Now your value will be maybe 3 10 to the minus 2. What you do, you put it in again. Next time your value will be the correct one, 2.9 10 to the minus 2. In fact, you should repeat this until you have a value that doesn't change anymore. That is why it's called stepwise method. So, and it is in the end, this will be less work than doing it with this special calculator and solving quadratic equation. So stepwise method. First, we calculate as 3.5, 10 to the minus 2. Then we use this for x. We calculate this x again by the square root. We will have the value which is almost correct. This value we use again for x. And then we will have the value which will be very close to the correct solution. And we can repeat until we remain constant. So this is a very easy way to solve it if we assume that we cannot simplify. When we have to decide about simplification and when not. So 1%, 2%, 3% is okay. I don't think it will make much of a difference. 35%, that's certainly too much. In that case, we need to use this iterative method. You see, the value 2.9, 3.5, it's too far apart. That's too big mistake, I think, to accept. So we need certainly this stepwise method in this case. If we would use this value points 13 in S or X in the iterative method, you will see it makes no difference. It's the same value. And so it will still remain 1.310 to the minus 3 if you would use it as X. That's, maybe the fourth or the fifth meaningful number will change, but that's it. Okay, so what happens when we mix one acid with the other? As you can see then, in the same solution, we will have two equilibria. But these two equilibria are not independent from each other. Because as you can see, both ionizations are generating H3O+. So we have some effect, of course, of then one onto the other. So we can think about the law of Le Chapelier. So if you add one of the products, that means you actually move back to your reagents. So you could say one ionization suppresses the other. And this is called common ion effect, or same ion effect. So if in two equilibria you have the same ions, or the same substances, the one equilibrium will influence the other. So, of course it will very much depend on how strong is the acids that you have added. So if we have two strong acids, actually it doesn't really matter too much. The two will behave as if they are independent of each other present, and they both will ionize completely. So you can just, in that case, easily calculate. You assume complete ionization. You add up the concentration of H3O+, you take the negative logarithm, and you are finished. Now, let's look at a mixture of strong acids and weak acids. So, a typical strong acid is HCl, and the weak acid is the one like we saw previously, acetic acid. So, 0.1 mole acetic acid. That's the same concentration as we just calculated in that previous exercise. So we will see what is the effect. So this is again the reaction equation. So acetic acid is reacting with water and giving its proton forming H3O+. We form acetate, and the thing that is different now is that we have already from the beginning 0.1 mole of H3O+ present. So now parts of the acetic acid will be deprotonated. Let's call it X again. What is remaining is 0.1 minus X. How much acetate is forming? The same small amount, X. How much H3O+ is present? 0.1 plus X. We can already think that there will be room for simplification, because probably 0.1 is going to be very big as compared to X. Okay, let's look how then it looks like. The equilibrium constant for acetic acid is still the same. It's 1.8 10 to the minus 5. The product is X multiplied by 0.1 plus X and divided by 0.1 minus X. Now 0.1 plus plus x of 0.1 minus x, that's just 0.1. Because x is so small, it doesn't matter if we add up or actually subtract this very small number exponent. So it's 2 times the same. This means we can remove it, and what is left is just x. We have finished this calculation. That's it. We don't need to calculate anything. Just in this case, we have the concentration is the same as the equilibrium constant. So that means the total proton concentration remains 0.1. So the simplifying is certainly correct, because this is 4 orders of magnitude, 1 in 10,000. So that means only the 4th significant number, maybe the 5th, will make a difference. So I think we can certainly do the simplification. The degree of ionization now is 1.8 10 to the minus 4. Previously, without the hydrochloric acid, it was 0.013, which is 1.3 10 to the minus 2. So that means now our conversion of the acids is 2 orders of magnitude, a factor of 100, less ionized because of the presence of the strong acid. So the statement of the strong acid suppresses the ionization of the weak acid is certainly true. In this case, ionization of acetic acid is suppressed by the strong acid ACl. So I think for today we will finish. I remain here a couple of more minutes for people who would have questions, and we continue with acid-base equilibria tomorrow. I believe we have 2 hours left tomorrow morning, and I think we will be able to finish our study of the acid-base equilibrium then.